Welcome everybody to the OptiBPM Introduction webinar. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your presenter, Steve Dodds. Before we begin, let's review the webinar layout. During the presentation, I'm going to launch 3 polls in which each poll provides Steve with useful information for guiding the presentation. If you are present for all 3 polls, your name is going to be entered into a $50 gift card draw, in which we will randomly draw at the end of our session and post the results on the website. We're also going to have 2 Q&A periods, the first one at the halfway point and the second one at the end. So you can go ahead and type your questions into the questions section of the GoToWebinar control panel, and we'll try to answer some of them while the session's in, while Steve's going ahead and doing the session, and the other ones that we're going to answer at the midsection and at the end of the webinar. So I'll go ahead and I'll answer as many as I can while Steve's presenting, and then he'll go ahead and read the more technical ones at the 2 Q&A periods. If for some reason we cannot answer your question during the webinar, we're going to go ahead and jot it down and get back to you afterwards. If you'd like to keep your question completely private, you can also email support@optiwave.com, and we can respond to you later. Lastly, we'll be recording the webinar and distributing it to all registrants via a download link that you'll receive in an email tomorrow at this exact same time. In order to access the recording, you'll need to use the same name and email that you used when registering for the webinar. So I'll now hand it over to your presenter, OptiBPM Product Manager, Steve Dodds.
Thank you, Brian. Sorry for the slight delay in our presentation. Minor technical problem. I think that's past us. And I believe you can see my screen now. Welcome to the OptiBPM introduction. OptiBPM is a software that permits the simulation of the propagation of light in optical fibers and optical waveguides. And what I'd like to do today is show you a typical design and simulation session in OptiBPM. When OptiBPM starts, you see a blank screen. It's nothing written in it yet. And the way the session starts is it needs to know what the geometry of your device is. So you can click on New, and it starts asking you a bunch of questions about your optical waveguides. For example, here the width is specified as 4, so that means that if I draw an optical waveguide, it will by default be a width of 4 microns, and it will interpret that waveguide as being defined by a predefined profile. Wafer dimensions refers to the definition of the space in which we will do our simulation, our design and our simulation. So this means that we have an 800 micron length and a 40 micron width, and that's the dimensions of say, the mask. And in the third dimension, we're asked to specify a material that the cladding will be made of and another material for the substrate. This could be any of materials that you've defined so far. For example, the cladding could be air. In the case where this cladding and substrate are the same material, this is going to lead to a buried waveguide. Incidentally, we have another window, the Profile Designer, in which materials are defined. You can see that we have defined a material called silica cladding for the cladding and core. And if we look on the list here, we can see what that meant. Silica cladding was simply dielectric, which was specified by giving a refractive index for it. In this case, it's 1.48. You can specify all kinds of materials. Here you give it a name, you call it something else. One could specify the material property by simply writing a refractive index here. It can be done in other ways. It could be done instead through a Sellmeier formula. In that case, I would enable the Sellmeier definition, and that would open to the definition by a Sellmeier formula, in which case one can put the numerical values of the wavelengths and amplitudes of the oscillator strengths to get a definition of material this way. If it's done this way, you can pop up the refractive index viewer to observe how that refractive index would change with optical wavelength. So that's a possibility. I'm not going to use it in this simulation. If that material were anisotropic, instead of specifying a refractive index, you would specify a permittivity tensor. By default, it simply fills the diagonal of permittivity tensor with the square of the refractive index, but you could write other values in the off-diagonal elements if you want. So this is how materials are specified. It's got enough information to start. And it presents you with a space in which you can draw waveguides. And there are CAD tools available that can help you with that. For example, one can snap to grid. That's sometimes helpful. You can select a bunch of different shapes of waveguides. If I put a linear waveguide here, I can draw it like that. What we're looking at right now is the plane that would define the mask. I can draw a bunch of waveguides here. So the horizontal direction in this drawing is the direction of propagation. And usually in waveguide work, the direction of propagation is Z. And the vertical axis, we choose X for the vertical axis. And Y, therefore, is the direction that's perpendicular to the screen. So doing a little bit of drawing here, there's a bunch of things we can draw. And after drawing some things, some shapes here, oh, I didn't want that one. I wanted this one. Draw some shapes to draw the shape of the device you have in mind, and it is the mask that you're dealing with here. In fact, when you're done with all of your drawing, you can actually export this to mask. It will come out in AutoCAD DXF or Calma GDS2, and you can export that into your favorite mask layout software when it comes time to fabricate this device. But in the meantime, we are drawing mostly for the purpose of simulation. We're specifying a geometry, and we're going to put some light onto it and see what happens with the propagation. This is probably a good time to save our project. This is Monday, so I'll call this project Monday. And thereby we can return to what we've drawn at a later time if need be. And I'll keep drawing. You can see that I seem to be drawing something that would be a splitter. My idea is to have light come in at one end of the waveguide and then split into two. But if you've done any work with optical waveguides, you know that this isn't a foregone conclusion, that you could draw something like this and find that the light just keeps going on in its merry way, or that it just gets completely messed up and does not follow the waveguides. And it's hard to predict in advance what the light will do. You don't really know what the light will do in advance without doing some kind of in-depth numerical simulation, and that's what OptiBPM does. So I've drawn what I hope will work as a splitter in the mask view. And we can go to the 3D editor now to take a look at what we've done in a 3D view. Let me make this bigger, make this window a bit bigger. Yeah, so we can see in a 3D view what we've done. And look closer, move farther away. So it gives you a general idea, and you can see what I've been doing is drawing channel waveguides, and my cladding is y is less than 0. Oh, sorry, my cladding is y is greater than 0. My substrate is less than 0, and I set the material of cladding and substrate to the same thing. So this is a buried channel waveguide. Another important way of viewing the structure is to look at this in just the XY plane. So that's there's Y. Y is the green axis, X is the red axis. So we can look in detail at the XY plane. This shows us that in the center we've got a refractive index of 1.5. That's what the core index was set to. And the cladding was set to 1.48 as I showed before. Right now, we're looking at the cross section at this distance. This is the very beginning. And as we progress in the direction of propagation, eventually you'll see the refractive index start to widen. This is where the Y splitter was taking place. Then it splits into two waveguides, and that's what happens to the end of it. So it's good to observe the refractive index in the XY plane to see it in detail as well. Okay. Now we have specified the structure of the device to model. The next step is to put some light in here. And to this end, we put what we call an input plane. This is a plane because it's extending along x, the entire length of x. But by this red line, it's meant that it also extends all through the y direction. So this red line is a plane in the xy plane. And to specify the light, it's our job to specify what the optical electrical field will be all in throughout this xy plane. Because the way the beam propagation method works, you see, is this method says if you know what the electric field is on one plane, here the dark red plane, and you know the refractive index of the space immediately to the right of the input plane, the beam propagation method will permit you to find out what the electric field is going to be on the next input plane. So starting with one at the left, the beam propagation allows us to find the electric field at another plane immediately to the right. And now that I have found the electric field on the plane immediately to the right, I'm now able to repeat the process. Now I know what the electric field is on the middle plane. Now I can use the beam propagation method again to find out what the electric field is going to be at the next plane. And I just progress all the way through the structure from left to right to find out what the electric field is going to be everywhere. But I do need to specify what the structure of the waveguide is, and that's been done. And I do need to specify what the electric field is going to be at least one input plane. To do that, we have a sequence of dialog boxes to help out with that. There's a number of different ways of specifying the electric field in the input plane. You can specify it as a Gaussian distribution. Gaussian would be used if it so happens that your input plane happens to be on the edge of the wafer, right on the edge, and you are illuminating the waveguide with a laser or something that would create a Gaussian-shaped spot somewhere on the wafer. And in that case, it would make sense to use a Gaussian excitation, optical excitation. More common than that choice is modal. And the reason that modal is popular is because usually the optical source is somewhere very far away from this input plane. Usually it's someplace much farther to the left, some source that created light of some form. Maybe, but even if that form was of single wavelength, it might be propagating in all directions. But the assumption is that it was waveguide propagation that brought it to this point. And if that's the case, then chances are by the time the light gets to this input plane, it's already developed into a modal form of propagation. And so our excitation is going to be modeled best by doing some mode solving on the input plane to find out what the optical field distribution would be for that. And we have a sequence of dialog boxes to help with that route. We've got, we say it's modal. We go to input fields, and that presents us with a list of waveguides on the right panel. In our design, there's only one waveguide in the input plane, but that didn't have to be so. I could have had a number of waveguides crossing the input plane. If I had done that, the entire list would appear in this right-hand panel. And then it would be up to me to select which of these waveguides have light. And if so, what is the amplitude and phase of that light? I only have one waveguide, so I can just select them all. There it is. And by default, OptiBPM said, we're going to take this mode of light. We're going to set an amplitude of 1 and a phase of 0. And that's how we're going to specify our input plane. So once we have found the optical fundamental mode on this waveguide, we know how to set the amplitude and phase. Now the optical electric field on the input plane will be specified. Along this path, we can go in to look at the actual mode itself by bringing up a mode solver to calculate mode. Oh yeah, at this point we have a choice. We can choose what kind of mode solver we'd like to use to find the mode. ADI stands for alternating direction implicit. This is a mode solver that's actually based on the beam propagation method itself. It's fast and for fundamental mode quite accurate, so we put that one up by default. We go to calculate mode, and we can specify a number of different choices here. We could find a full vector mode or semi-vector modes of different polarizations and a bunch of other settings specific to mode solvers. Here it reminds us that we set our wavelength to optical wavelength to 1.55 microns. We can ask to find more than one mode if we like. We could ask it to look for 2 modes. And now I'm ready to call the mode solver itself by pressing calculate mode. And it presents us first with what it saw as the refractive index distribution. You've seen this picture before. Then it found the optical mode that would exist on this waveguide. It does appear that the majority of the light is parallel to X. There's the EX component. There is a small fraction of light in the other component, in the Y component. It's quite small. And this is the modal index of the mode that's been found. It's a little bit higher than the cladding index. It's somewhat lower than the core index. It went looking for a second mode, but did not find one. There's a good reason for that. That waveguide at this wavelength is a single mode waveguide. There is only one guided mode on it, and it looks like that. Okay, so it found a mode, and we're happy with that. We say OK to all of that. And now we're ready to begin a simulation. We're going to do a simulation of 3D, this isotropic material it is. We start the simulator, and away it goes, and it asks if we want to use OptiBPM Analyzer to view the result, which we do. The analyzer is a separate, dedicated application. It makes a copy of the of our of a layout that we drew. If we go to open, this is the one we are doing right now. These are other simulations that I did before. They can be opened as well. So this is a place where you can come back and view simulations that you did before without having to do the simulation again. And we can see that the splitter is functioning more or less as expected. We are getting light that is concentrated in a modal pattern at the beginning. It does seem to split into two fairly cleanly, and all's well. And at this point, it's a good idea to look at the phase view of this. You're looking at the amplitude of the envelope function. But it's good to look at the phase as well to see if the reference index was chosen properly. Here we can see that the phase is not changing too abruptly in the places where we have optical power. So all is well with this simulation. Right now, I would like to take a break in our presentation to give me a chance to read some of your questions. And Brian would like to submit a poll to you to ask you a few questions too. So take it away, Brian.
Okay, so the second poll is up, so if you guys could answer that for us while Steve takes a quick break here and checks to see if there's any questions that we can answer right now. And just to remind you, we can answer the questions during the session, or if you have questions that are a little bit confidential that you'd rather not post to the group here, we can handle those via support@optiwave.com. Okay, Steve, I'll pass it back to you. Is there anything that you wanted to try to handle right now?
Yeah, all's well here, Brian. 3 questions, and I will answer them all.
Perfect.
Thank you, Brian. Now I'd like to take a moment to answer a few of your questions. First question is, can we demonstrate plasma dispersion effect using OptiBPM? And the answer to that is usually no. And the reason being that the beam propagation method is a paraxial method, and it means that paraxial is one of the approximations employed in using the method, and part and parcel of that is some restriction on the refractive index contrast that is tolerable. I showed you about how the beam propagation method works. It works strictly from left to right, and from that you might be able to guess that it's not going to do reflections, and that is connected to refractive index contrast. In plasma type materials, there's very large refractive index contrast, and usually that means that it's just outside the scope of the beam propagation method, especially if the contrast occurs in the direction of propagation. It's not to say that it can't be done. In fact, I did it once, but probably not. If you've got materials like that, you're probably looking at a finite difference time domain method as your method of choice. Another question is, the designer has got a bar with different colors in it. What does that represent? All right, I'm prepared to show that. In the 3D picture of our waveguide, these were all channel waveguides, but they don't have to be. Selecting each waveguide one at a time here, I could select this one, for example, and bring up its properties. And here is listed its the position of its starting and ending points and a bunch of other details about this. One of the details is, what is the profile being used? Here, it is a channel profile, but if I change that to a different kind of profile, a fiber profile, like that, then what you'll see is now the waveguide that I changed the profile is represented with a different color. And this is to indicate, when we're in the layout view, that the waveguides in green are one shape, but the blue waveguide is a different shape. In the 3D editor, you can see in detail what this means. The waveguide that I changed to a fiber, it looks like a cylindrical shape now, and that's how we would simulate optical fibers in OptiBPM. Or if you did have some problem that had both channels and fibers in it at the same time, you could still do that too. Question 3, how to optimize the parameter of power divider? Well, I'll just give a brief overview of that. I'm not going to do a demonstration of the optimizer, but I'll give you some clue. Any parameter that we have here, this is properties of the selected waveguide. Anything that we specify here, maybe say position or width or depth is its position in Y. All of these have a little f of x box beside them. What this means, if I click on it, is it brings me to a variables and functions dialog box, and here I can define a variable of my own idea. I can put a value next to it. And now if I write in this space here, in the blank space here, if I write my variable, it will take whatever value this thing happens to have at it will take whatever value this thing happens to have at the time. That's useful by itself if you happen to have a lot of things that you would look to change at the same time. You can assign them all to the same variable and change everything at once. It's also useful if you want to do some kind of optimization. And if we want to do an optimization, then the variables to optimize can be selected and put in, and we can run through a list. There is an optimizer, but I don't have time to show it today. But that can all be done, and there are examples of that in the tutorials and in the sample files But briefly, that in a nutshell, that's how it's done. You parameterize the design. You allow the parameters to go into the optimizer. You define a merit function using the script and let the optimizer grind away. Okay, on with the show. I would like to show you a few more features about OptiBPM. I showed you the analyzer, and you could see how data was appearing in the analyzer. There's a lot of things that the simulator creates which only go into the analyzer if you ask it to, because there's just so much generated. You really do have to control what goes there. So I'm going to show you a box that controls what data you want to appear in the analyzer. The relative power versus distance is always a good thing to see. This is how much optical power actually exists at each slice during the propagation. This will tell you how much optical power has left through the simulation boundary windows. There are transparent boundaries on all sides. Power and output waveguides is another useful thing. When the simulation finishes, it's going to find the fundamental optical mode on the waveguides that leave the wafer. It's going to do an overlap integral of the optical field at the end of the simulation with the modal field pattern, and thereby determine the modal power that's coming out of these waveguides at the end of the simulation. Another useful feature is Z-cut. Here you can specify any distance where there's something interesting going on. For example, for us at a distance 300, like in around here, this is when the waveguides have just split apart. And we might want to see in detail what the optical field looks like at that point. We might want to see what the optical field looks like at a much later point at 750, after we can expect that the fields have settled down somewhat. So I'll show the field pattern there as well. So when we run the simulation again, we're going to get these additional data in the analyzer as well. So let's run the simulation again. Oh, there's another difference now. One of our waveguides is a fiber, not a channel, so that'll make things different. Yes, we want to go to the analyzer. Yes, we're done with the simulator. And this is what the optical field pattern looks like now. It appears that the optical fiber-like shape stole most of the power. We can look at, we asked for the power in the output waveguides, and here it is. This graph is set up to accommodate multi-iteration simulations where you run the simulation many times while changing a parameter or something. We only did it once, so there's only iteration 1, and these are the two powers that came out. We can see in detail from export. Here it says that the waveguide called linear 3, which for the sake of memory, linear 3 is that waveguide. So it looked like quite a lot of power went to linear 3. The other output waveguide was linear 2. Linear 2 is that one, and only 17% of power went to linear 2. So that's the power and output waveguides. this is the relative power versus distance. This is the length of our propagation. The total length of propagation was 800 microns. It started out such that the normalized power was 1, and as the propagation went on, we can see that by 700 microns or so, we had lost 20% of power, had left the simulation boundary windows from top or bottom. And this is the z-cuts as I promised, and here we are at the distance 300. There is, with the two waveguides had split, 300 is about here somewhere. So there is the channel on the upper side, and there's the fiber on the lower side. And later on, at 750, by this time they were, again, both channels, but looks like the lower one stole most of the power. And another thing that we can see, since we selected this lower waveguide to be a fiber, is that if we look at a place where the fiber comes into view, we can see that what we actually see is the refractive index after applying the mesh. So it doesn't look exactly like a circle because it's simply approximated a circle by applying a mesh, so you get a staircase approximation. So this view is useful if you want to find out what are the mesh parameters I should apply. I would get a more accurate representation if I could increase the number of mesh points. If I increase this to 300 mesh points, if I increase that to 300 instead of just 100, and I refresh the view, now it looks much more like a circle, but you'll notice that running with this many mesh points, the simulation will run more slowly. So it's up to you to decide exactly this particular trade-off. Okay, this concludes my technical presentation. I might have time for another question. Let's see what else we've got.
So while Steve takes a look at the questions, we do have a good number of questions that came in. I'll launch the last poll here that you guys could respond to, please. And as mentioned earlier, if we can't answer the questions during the actual webinar, we'll go ahead and email you guys directly afterwards. And just as a side note, there are spaces now available for all the sessions. We upped our capabilities for the GoToWebinar, so feel free to register for as many additional sessions as you'd like. The same page that you guys are registering for the sessions, this is where we're posting the winner of the $50 gift card draw. So you should see the announcement for that around noon today. I'll pass it back to you, Steve.
Okay, thank you, Brian. More questions. One question from Sergey was, could you please show the phase difference? I'm sorry, Sergey, that I don't know exactly which phase difference you mean. This does show the optical phase of the envelope function. I'm not sure that's what you meant, but if it's not, you can send a more detailed question to me later, and I will answer. Another question is, how can I design a single mode fiber with air outside? Well, what we would do in that case is I showed, oh, this is analyzer. I want to go back to designer to show that, so I have to open the designer again. Bear with me. There it is. Let's open up a designer again. Let's open Monday, come back to Monday. I showed a design where the cladding and substrate were a material of my specification. But if I changed those to air, then we would have air outside the waveguide and outside the fiber, and then the simulation would go according to air and not to a cladding material. Bear in mind, though, that if using air, you are a little bit limited because this will create a large refractive index difference, which is sometimes tolerated in the transverse direction, sometimes not. You should show us details to get an educated opinion on that if you're not sure. Another question is, can we demonstrate modeling photonic crystal fiber using OptiBPM? The answer is yes. I don't have an example ready to go for you, but we have done this with success before. There is a question of someone's having trouble with their license server. Problems like that, simply send an email to support@optiwave.com and we'll take care of it for you. Another question is, can we model active optical devices using OptiBPM? The answer is usually no, and the reason for that is that the beam propagation method is a single wavelength method. Active devices have the property of being changing in time, which will move light into an optical sideband. And now it's outside of the scope of the beam propagation method as we've implemented it. I took some care. Another question is about taking some care to draw the optical waveguides outside the limit of the wafer. And yes, you're right, that was deliberate. And the reason is the following. Let me try to show you what happens. Let's go, let's show the properties of this. Let's put the end of this exactly at the end of the wafer, which occurs at coordinate 800. Let's do that, and let's put the end at coordinate 800, but make the offset just something slightly different, make it 0. So it does that. And let's go and look at what the refractive index profile is there. Okay, all's well here at z is equal to 0. All's still fine here. And then we get to 800. Oh, suddenly this is half the width. Why? Well, it's hard to see, but if you zoom in about a zillion times, you'll find that the waveguide is only half the waveguide actually extends over the end due to the angle. People get stuck on that sometimes, so I just played it safe by sending it off the end. If only half the waveguide is presented at the end of the wafer, it might look for a mode there, not find one because it's not the refractive index distribution of the entire waveguide. Can we model erbium doped fiber amplifier? Not in BPM, but OptiSystem does have some capacity to further modeling of erbium doped fiber amplifier. For the input plane, a question about what kind of file can we use to define our input beam profile. You use it's an ASCII file. It's prepared in OptiWave format, and our manual does specify precisely what that format is. So create an ASCII file and write in there what the optical field is, and as long as you've prepared it in the correct format, OptiBPM will read it, and away we go. Do we have wide-angle capabilities in OptiBPM? Yes, we do. The anisotropic simulator in particular has them. If you select the Crank-Nicholson method, wide angle is not available in alternating direction implicit method, but in the Crank-Nicholson method, we've got some higher level Pade orders that permit wide angles BPM simulation. You want to import a GDS, someone else wants to import a GDS file onto the layout. That's fairly simple. In File, you go Import and say from mask, and then find a GDS file, which I don't happen to have at the moment, but if you do, in it goes. Job's done. Someone else wants to design a channel waveguide which is made from lithium niobate diffused with an annealed exchange fabrication process. And yes, we have something for that too. In here, it comes down to in Profile Designer, I'll show that. You can see it in the Profile Designer. Materials, it could be, instead of a dielectric, it could be a diffused material. And here you're able to specify a lithium niobate type diffused material. And the profiles themselves have a number of different diffusion processes available. One of them is a diffusion process by proton exchange. And in this case, a waveguide defined this way, you'd specify the waveguide in terms of process parameters. It would appear as a waveguide of different profile, and any waveguide labeled this way would be a graded index waveguide according to the diffusion specified from the process. And that seems to answer. I've answered all the questions that I'm able to right now. If I didn't answer your question, please submit it by email, and I'll have a go. And that is the end of my presentation. Thank you very much for dropping by.